right. Well, happy Wednesday, and we'll take a look at what we got today. So, well, I'm kind of excited. I'm gonna introduce neural networks as a topic. Okay, and but before we get into that, because gradient descent is going to play a role here. Oh. As soon as I try to adjust the volume in the classroom, it turns off the projector. Okay, I will. That is frustrating. Okay, well, I'm quick review of gradient descent. It says, I guess you'll have to look at your slides, and then hopefully the projector will turn back on. Okay, so that seems to be an issue here, maybe. Okay, what we're trying to do is we're trying to find values of W. So W being our vector of weights in our, for our function. Okay, so we have a function that calculates loss. We treat the data that we have as fixed values. We adjust the values in our weight vector, and that function calculates the loss. And so depending on what weights we have, and so far we've seen things like we've seen values for like changing the intercept and changing the slope, and we could see how that would affect the loss function. Okay, and basically when we do something like neural networks, it's the same idea, except rather than just having two parameters, one for the intercept and one for the slope, you now have like maybe well, we'll look at a very simple neural network with maybe like 20 parameters or something, and then but like a complicated neural network might have like 1 million or 1 million of these weights. Okay, but in essence we're still doing the same thing. We're just changing the knobs, tweaking all of these knobs, okay, and we're trying to find what combination of knobs will lower the total loss. Okay, so gradient descent, the way it works is we start at some arbitrary location, and then how do we select what location we move to, right? And the way it works is it says, okay, well, let's find the gradient at our current location, and the gradient points in uphill, going the direction of steepest descent, and we just move in the opposite direction. So gradient descent says, okay, if you're currently at location, this location at time n, your location at time n plus 1 is just your current location minus the gradient times some kind of scaling factor. And I don't know if you've taken a look at this week's homework, but you'll kind of mess around with the gradient there. Okay. All right. So this neural network stuff. How does it all work? A lot of my lecture is based off of this series of videos on YouTube from Welch Labs. 3 Blue 1 Brown also has some videos on neural networks, and I don't know, neural networks, they've technically been around since like 1970, the 70s and whatnot. And honestly, like they've gotten super popular in the last decade or so, and a lot of that is because we have the computational power to train a more complicated neural network. Okay, so in our class, we're going to kind of deal with the simplest kind of neural network, the kind that's been around since the 1970s and 1980s. And to be honest, the neural networks that we use today have very similar structures, except we've just grown them in size. Okay, so it's kind of just like, imagine the kind of neural network we have today, but rather than like just one layer, we'll talk about what these layers are. You make like 1,000 layers, and each layer will have, or maybe not 1,000, but I don't know, a few hundred layers, or yeah, possibly 1,000 layers. And then rather than having only a handful of nodes in each layer, you have like thousands of nodes in each layer. So you have, this very, very, very complicated thing that nobody really understands anymore. But we have the computational power to kind of train this very complicated network, okay? But we're just going to deal with kind of just the miniature version of it, the small version, and that's what we'll have, okay? Because our simple one and the complicated one, it's the same idea, and it's just, we're using gradient descent, okay? What is a neural network? So in an overly simplistic sense, a neural network is a design for a function, meaning that you get inputs coming in, it does calculations, and then spits out an output, all right? The inspiration behind a neural network and why we call it a neural network is, I guess, the brain. If you look at the brain, you have like neurons, they're all kind of connected. You have these synapses, and basically, a neuron receives an input signal, like a little electric pulse goes in, and then depending on that particular neuron's function, that neuron might then activate and send an action potential, or basically another pulse, to the neurons that it's connected to. And basically, as you're sitting here, like millions of these things are just happening every, fraction of a second, and that's how you're processing information. That's how I'm speaking, and all of that, right? And we have neuroscience, and so we have like a general idea of how some of this is working, but it's also like still a lot of mystery too, okay? And when we make a neural network on the computer, it's basically a bunch of these tiny little, tiny isn't really the right word, but just we got nodes. The input values come in, and depending on the input value, depending on the node's activation function, the node will then kind of send out an output value to other nodes that it's connected to. So we'll start off with this very, very, very simple example, okay? Our input matrix X has two columns, and I'm just kind of using the same example from the Welch Labs video. If you watch those videos, we have two columns for the input matrix, and we'll just call these hours of sleep and hours spent studying, and then the output Y is going to be the exam score, okay? And we have 3 observations in our data. So we have 3 rows in X and 3 values in Y. So that's that, okay? And the way it's going to work is we've got all neural networks start off with an input layer, they end with an output layer. And so because we have 2 columns in our X matrix, we're going to have 2 nodes in the input layer, okay? 1 node for basically each variable in X, okay? And then we have 1 value that we're trying to predict. In our case, it's the exam score. And so our output layer is going to have 1 node, okay? Now, in a future example, we'll have a neural network where there's multiple nodes in the output layer, but it's the same kind of principle there, okay? A neural network will also have at least one hidden layer, possibly more, okay? And, just for simplicity, we will have a hidden layer with 3 nodes. So very, very, very simple network, okay? And, the choice of how many nodes that you want in your hidden layer and how many hidden layers you want is kind of an arbitrary choice. I'm choosing very small numbers, like 3 nodes and 1 hidden layer, just to keep our introductory example, really simple. And so the layers go input layer, hidden layer, output layer, okay? You can design something to go input layer, hidden layer, hidden layer, hidden layer, output layer, right? You can have a bunch of these hidden layers in a row, right? And that's, and so this is what our neural network looks like. Okay, we got 2 nodes for the input layer, hours of sleep, hours of study. All right, I've got 3 nodes in my hidden layer, and then I got 1 node in the output layer. And you'll see each node is connected to all of the nodes in the next layer. So from the input layer, I've got a connection from X1 to the 3 nodes in the hidden layer, and then I've got a connection from X2 to each of the 3 nodes in the hidden layer. And then from the hidden layer, this node connects to the output layer, this node connects to the output layer, this node connects to the output layer. If I had multiple nodes in the output layer, then each of these nodes in the hidden layer would also have their own connection to each node in the output layer. But right now I just got one in the output layer. Okay, so you have things like deep learning. Okay, and deep learning is a popular thing just because it's these deep learning networks are really good at predicting stuff. And basically you have 100 more, possibly thousands of hidden layers. All right, and that's where the deep part comes in. Okay, and these deep neural networks have been incredibly powerful. And now it's kind of almost like old news, in that the idea of, can a computer recognize what is inside a picture? That would have been like magic, okay? But now it's like old hat, right? You go on Google, you type in image search, and it does something, right? And then you take pictures on your phone, and your phone is already like saying, oh, this is a picture of dogs, right? Like you can now search your own photos that you've taken and say, show me pictures of cars, show me pictures of trees, show me pictures of stuff, and your phone like recognizes these things, which is really amazing and is possible because of these neural network algorithms running in the background and stuff. And I guess there was this thing called ImageNet, it's still a thing, but now it's almost like a solved problem, kind of like when a computer player beat Garry Kasparov in chess. That was like a revolutionary thing. Okay, and now it's like, oh yeah, everybody's phone can beat the best human player in chess now. Okay, and the idea of a computer labeling images was truly this remarkable thing. And then 2015, I guess that's 8 years ago now, the computers started outperforming humans as far as labeling images, right? Because they would show you this little picture and it would say, okay, what is this a picture of? And you had a whole bunch of options, and it would be kind of complicated. It'd be like, here's a flower, but you had to label like, oh, this is a daisy. This one is I don't even know the different kinds of flowers there are, right? And so humans would do pretty good, probably get like 96%, 97% on these things. And then, in 2015, the computers beat the humans and stuff like that. And really has only gotten better and stuff like that, okay? Basically, self-driving cars, all of these kinds of cool AI applications are neural networks happening underneath, right? The big thing right now are these like large language models for like ChatGPT, where you're talking and the computer is talking and it's generating all of this kind of stuff. And so we're not looking at generative algorithms. We're just ours is more like predictive, but a generative algorithm is basically the same kind of thing, except the output that it's producing, it's trying to produce like basically new input type of things, right? And so these are all kind of like modifications of neural networks. As far as we're gonna have just a couple lectures on this. We'll just look at the simplest idea, but again, everything is just kind of like an extended version of what we'll look at. Okay, so anyway, all of these neural networks, they're really good at making predictions. Okay, but they have no very little interpretability, okay? The function of each node often remains a mystery. And it's a little bit like neuroscience, right? We can say, oh yeah, humans are really good at like learning stuff and seeing patterns, right? You give a child, like a baby is able to pick up language and things, right? But then you ask like, okay, well, how does that work? That's like a much harder question, right? And so similarly, with a neural network, we could say, oh, it's working, right? The neural network is able to make these predictions and it's working. But then it's like, okay, well, how does this work? What does this node do? Like if we opened up someone's brain and we pointed to a single neuron and we say, hey, what does this neuron do? We wouldn't really be able to know. We can say like, okay, if I stab it, or I don't know what they do, right? But if we probe this thing, the person, like brain surgeries are done when the person's like awake, and you ask like, hey, are you experiencing something? And, they kind of poke this part of the brain and they're like, oh yeah, when you do that, like I'm hearing music, right? And so we're like, oh, okay, that's interesting, but it's not like anybody would have been like, oh yeah, obviously by looking at the structure of this, we know this thing is going to do something. And similarly for a neural network, after it's all trained up, we can't just point to this node and say, hey, what is this node doing? It doesn't work that way. You could like turn it off and you say, oh, now our predictive performance is dropping and stuff like that. But anyway, that's where we are. Okay, let me give you your first view quiz answer, which is the letter C. C as in cat. C as in cat. Okay, so here is our diagram again. 2 nodes in the input layer, 3 nodes in the hidden layer, 1 node in the output layer. Connections from every node to every node from layer to layer, right? So we have a total of 9 connections that we see, 9 arrows, 6 connections from the input layer to the hidden layer, right? We got 2 here and 3 here, so 2 times 3 ends up being 6, okay? And then we have 3 connections from the hidden layer to the output layer. 3 nodes in the hidden layer, 1 node in the output layer, 3 times 1 is 3. And so we are going to put a weight, okay? A weight on every single one of these arrows. Every single one of these connections gets its own weight. All right, and so we're gonna have, I guess, 9 weights. Each of those weights is loosely how important a connection is, but again, don't try to interpret any of this, okay? Don't try to be like, oh, the weight from node 1 to node 2 is 7, and the weight from node 1 to node 3 is only a 4, and what does that mean? It's not like slope and intercept where we can understand it. It will just say, okay, the weights are different, and that's really about it, okay? And when we say, we're going to train our model or train the network, we have these kind of phrases that we like to do, right? Like, oh, I've got to train my model, okay? Basically, what does that mean? Training the model here just means, what weights should I use? I've got 9 weights to figure out what weights should I use, right? And so you can kind of, imagine a whole bunch of these knobs now, right? And you're trying to figure out, okay, like how do I make this thing, work as best as possible? You turn this knob and like it has this effect, and then you go, oh, okay, well maybe that's not the best thing, right? And then you try turning another knob, and it's hard because you can try turning each knob one at a time, and but every time you change something, it seems to affect something else. So, but that's what we're going to try to do, and the way we're going to do it is via gradient descent. So here I've labeled all of these things, okay, and so let me just show you kind of the notation that we're using, and depending on what textbook you pick up, you pick up a textbook on deep learning or things like that, it might have slightly different notation. So but here we are saying, okay, the connection from node 1 in the input layer to node 1 in the hidden layer, so node 1 to node 1, that's going to be weight 1 1, okay? And then from node 1 to node 2 is going to be weight 1 2, and from node 1 to node 3 is going to be weight 1, 3. Okay, and then this one is weight 2, 1, going from the second node to the node 1. Second node to second node is weight 2, 2. Second node to third node is weight 2, 3. Okay, all of these have a superscript 1, kind of indicating that these all are in the first weight matrix. Okay, and then this is first node. There's only one node in the output layer, so it goes 1, 1. Second node to the first node is 2, 1, and then third node to the first node is weight 3, 1. And these all have superscript 2 to indicate that they are in the second set of weights. Okay, so to kind of, and then we arrange these in matrices. Okay, so we have the W1 matrix, which is the weight matrix from the first layer to the hidden layer. And then we have W2, which is the weight matrix from the second layer, which is our hidden layer, to the third layer, the output layer. Okay, weight 1, 1, the weight matrix 1, capital W1, has 6 values, 2 rows and 3 columns, because we got 2 nodes in the input layer, 3 nodes in the next layer, and we've arranged them like weight 1, 1, weight 1, 2, weight 1, 3, weight 2, 1, weight 2, 2, weight 2, 3. They all have superscript 1. Okay, and then weight matrix 2 has 3 rows and 1 column. Okay, three rows because weight the hidden layer has three nodes, and then the output layer has 1 node, so 3 rows, 1 column, and there will weight 1, 1, weight 2, 1, weight 3, 1. Okay, so this is how we label all of the different weights. Okay, and so what does it look like when we take our input matrix X and we multiply it by our weight matrix W1? Okay, so this is why linear algebra is like super important, because everything we're doing is matrices. Okay, so our input matrix X, we have n rows and 2 columns, and we're going to multiply it by our first weight matrix W1, which has 2 rows and 3 columns. So when you do n by 2 by 2 by 3 multiplied by a 2 by 3, the output is going to be n by 3. Okay, so we're going to have n values, or n rows, okay, 1 for each kind of observation, and these are all of the values that happen in the hidden layer, and so you got 3 values. So this is n rows and then 3 columns. Okay, and the value in the first column is basically x11 times weight 11, and then x12 basically the second value in the first observation times weight 21, and so on and so forth. Okay, we'll call this matrix Z, okay, and Z superscript 2 to kind of indicate, I guess it's our, second layer of values, or I don't know, okay. And then, so we have that matrix Z, and then we apply an activation function, okay. So we apply a function to each of the values in Z. So I've got, Z is n by 3, we're going to apply a function to each value, and so the result is going to be our activated values, and we just apply the function element-wise. Okay, so each element in Z, we apply the function, and so we're going to get another matrix with the same exact dimensions. It's going to be n rows, 3 columns, and these are all of the values after we plug them into the function. Okay, now what do we use for an activation function? We've got all kinds of choices. The classical choice is the sigmoid activation function, basically a logistic function. Starts off at 0, goes up to 1, looks kind of like this, and basically, at 0 you're at 0.5, and then once you go past x equal to 5 or something, you get something very close to 1, asymptotically approaches 1, and then once you're past negative 0.5 or something, asymptotically approaches 0. That's the sigmoid activation function. This is kind of our classical thing. It's kind of fallen out of favor these days, just because computationally there's some hangups that if for whatever reason you end up out here, your slope at this point is practically 0, and then the slope out, once you go, you might end up at negative 10, and your slope at that point is also practically 0, and that kind of can cause your thing to stall a little bit. But anyway, we'll just kind of use this. But again, maybe fallen a little bit out of favor. Neural networks today probably most commonly use what's known as the ReLU function, rectified linear unit function. There's a whole bunch of activation functions you can use, and you can go on Wikipedia and I don't know, you got a bunch of illustrations of these things, and so this is a popular choice, the ReLU, but sigmoid, where did it go? Okay, I don't know. Oh no, here it is. Okay, sigmoid, or the logistic function, is what we're looking at. But yeah, lots of choices. Okay, doesn't really matter. I shouldn't say it doesn't matter, but lots of choices for what you could use for activation function. We'll just use the sigmoid here. Okay, so here's all of our labeled connections. And then so once we have our activated values, okay, so again we have n rows, 3 columns. These are our activated values. Then we'll take those values, okay, so that you can kind of imagine they're all kind of residing in this hidden layer. And then what do? We multiply it by our second weight matrix. Our second weight matrix, 3 rows, 1 column. So when you do this, you're going to get a single column, right? N by 3 times 3 by 1 gives you an n by 1. A single column, it's a linear combination of all of these things, right? This times this, second value times the second value, third value times the third value, you add them all up into one value. So now you just have one column of n values, and that's going to be your Z3 matrix, okay? N rows, 1 column, and then once you have that, then you run it through an activation function again. In our network, we're using the same activation functions. I use the sigmoid activation function in the hidden layer, and I'm going to use the sigmoid activation function in the output layer. There's no requirement that says you have to use the same activation function. You can use different activation functions for each layer that you want, right? And then one of your activation functions could even just be the identity function, meaning you're not even applying anything to it, okay? So you got all kinds of choices here. Just kind of for simplicity, we're going to just use the same activation function for all of these things, and that's going to produce our output value. Okay, so putting it all together, we have our input matrix X, n rows and 2 columns. We multiply our input matrix X times our first weight matrix. That gives us Z2. We apply an activation function to every value in Z2. That gives us our activated values. Then we take our activated values and we multiply it by the second weight matrix, W2, which gives us Z3. And then we apply our activation function to all of those values in Z3, and this will be our final predicted values, okay? Here I've kind of written them out as like a sequence of steps, but ultimately you could also just write it as just one big function, right? You got X times W1 inside the function. We take that result multiplied by W2 and we put that inside a function, right? So we can just say our predicted values Y is just the result of taking our input values X and doing these operations to it. Okay, and that's what we have. This is what we call forward propagation, right? We take our values and we just kind of push them forward through our neural network. And if you have a deeper network with more layers, basically you just have more of these multiplication by some weight matrix and more activation functions. And the activation functions, could be any of your choices there, right? Okay. A lot of times, and so this is what if you watch the Welch Labs video, they kind of do this kind of stuff. A lot of times we want to include what's called a bias term. A bias term is kind of like an intercept term, right? You're just adding a constant, okay? So a lot of times we want to add some kind of constant to our values, okay? It's not quite an intercept. An intercept kind of slides it up and down, and the bias is actually sliding it left and right. But you might want to add some kind of constant to these things, and so you would have a bias value added for each kind of node in your hidden layer and in your output layer. Okay, so here I have B1 as the bias for the first node, B2 is the bias for the second node, B3 being the bias for the third node. Superscript 1, I guess, our first set of bias values to kind of go along with weight matrix 1. Okay, and then B2 is B1 is our bias for the one and only node in our output layer with a superscript 2 to show that they kind of go along with our second set of weights there. Okay, and so what we're basically doing is we're doing the same kind of thing. We do x times W1. This gives me an n by 3 matrix, and our biases, okay, depending on how, so how do you store your biases? I'm going to store my bias values in a 3 by 1, 3 rows, 1 column, okay? And in order to kind of get this to apply, I'm going to transpose that into a row, a 1 by 3, and then I'm going to multiply it by a column of 1s. Okay, that column of 1s I'm going to call J. All right, and that's to get this to align so that, because x times W1 is an n by 3, and I need to add an n by 3 matrix in order for the dimensions to line up. So I need just a column of 1s, which we'll call J. And basically, that's just going to take our row and basically duplicate our row across all n rows. And that's how we're going to get our set of values z. Okay, and then we run that through the activation function. All right, does this kind of make sense? I'm transposing the biases. Now, again, how you decide to store your biases might differ from like textbook to textbook. So some might say, oh, store your biases in a row matrix to begin with, then you don't need to do any kind of transposing here. But here I'm storing the biases in a column, and so I have to transpose them. Okay. So this is kind of what it looks like. So this is your J matrix is n rows, okay, and it's just a column of 1s. And so basically, if I do 1 times B1, B2, B3, I'm going to get B1, B2, B3, B1, B2, B3, B1, B2, B3. Basically each row is just B1, B2, B3, B1, B2, B3. Okay. And so this gives me, n by 3. This gives me n by 3, and I can add those two, right? And so now I have the combination of these things. I tried to color coordinate all of these things. This was, I want you to know that it was a pain to do, okay, to do this in LaTeX and color code each of these things. So please appreciate the the efforts that I put in to do this. Okay, so anyway, that's what we have here. All right, and then you activate all of those things, right? So now we have activated values. N by 3 activated things. We do our same thing. We multiply it by our second weight matrix W, and then here B2 is just a single value. So it's kind of silly that I'm transposing this, but just to kind of stay consistent, in case you had like a whole bunch of these things, you would have to transpose the column into a row. You'd multiply it by that column J, n by 1, and then basically add all these things up. And so even if you're doing this, you still just get one column of values. It's kind of a bunch of values added together to get that one value, but it's just a single column of values, n by 1, right? And this is going to give us certain things. And then we run this through the activation function. Okay, so if you have bias terms, then the thing is, x times w plus your bias terms to give you your z values. You run your z values through your activation function. Then you take your activated values multiplied by w2, and you add your bias terms to get z3, and then you run z3 through your activation function to get your predicted values y hat. Okay, and so even though it seems more complicated, it's not that much more complicated, and you have this. Okay, but now you have so for the one without the bias terms, you had 9 values. We had 6 weights in W1, 3 weights in W2 to estimate. And for this one, you would have those 9 plus another 4, 13 values to estimate. You'd have another 3 bias values to estimate and 1 bias value to estimate. So you'd have 6 plus 3 plus 3 plus 1 for a total of 14 values to estimate during your training process. Okay. Let me give you your second view quiz, or how many? Okay, so you know what, let me just give you your last two. Last 2 view quiz answers are D and A. D as in dog, A as in apple. D as in dog, A as in apple. Okay, so how do we train our network? Okay, the way we are going to train our network is we have to compare our predicted values to the actual values. Okay, and so our loss function is going to be the sum of squared errors, or the mean squared error, or whatever we want to do. Okay, so here I'm going to just say my loss function is the sum of squared errors. So this is, you know, we're still in this supervised learning. We'll talk about unsupervised learning later, but supervised learning just means you have your input values and you know what the answer is going to be, right? So we can, you know, when we train, so if I go all the way back here, I'm going to use these observations to train it, right? I have this input 3 and 5, and I know that when I plug in 3 and 5, I should get an answer. If my model is working well, I should get an answer that's close to 75. When I plug in 5 and 1, I should get an answer that's close to 82. When I plug in 10 and 2, I should get an answer close to 93, okay? And if I get answers that are not close to these things, I'm going to say I need to change my weights to get us closer to those answers, okay? And so we measure our performance by taking the difference between y and y hat, okay? And so, you know, I can just do, you know, I've got in matrix form, I got, you know, y minus y hat, and rather than having to do the summation here, I can just do y minus y hat transpose y minus y hat. And I think we would see that doing this is the exact same as doing each individual value y minus y hat, squaring them and adding them all up, okay? It's just that, okay, what is our y hat? Our y hat is the result of kind of this operation or this complicated operation. And we have the task of figuring out, okay, what are all of the different values I need to be using in W so that y hat is as close to y as possible, okay? And so what we will do, I guess, in our next session is we are going to do gradient descent, okay? We are going to figure out, right? So now I have this, again, when we do, how does gradient descent work, is we have our training data and we treat that as fixed, okay? So a lot of times as our functions, we think of like, oh, you know, if I plug in x, I'm going to get this y hat, right? But our x values that we've observed, we're going to treat that as fixed. The y values that we're supposed to get, we also treat as fixed. And the things that we get to change are the values in W, right? And so, but you know, I have 9 of these things. How do I know which one to change, right? And so, you know, we could do like coordinate descent, but here we're going to do gradient descent, which is going to say, okay, what is the gradient, all right? Which is the direction of steepest descent for all 9 of these things simultaneously. And it's going to say, okay, you know, go in this direction in 9-dimensional space. And we say, okay, I'm going to go in the opposite direction, right? So, you know, I currently have 9 values in this is a vector of 9 values. We're going to say, okay, what is my gradient for my current set of 9 values? And we're going to move in the opposite direction. Okay, so, and then next, I guess on Friday, what we'll do is we'll talk about how do we calculate the gradient, okay? And we have two gradients to calculate. We got the gradient for weight matrix 1 and then we have the gradient for weight matrix 2, right? If we have bias terms, we're going to have a gradient. We're going to have 4 gradients to calculate: a gradient for the first bias matrix, and a gradient for the second bias matrix. Okay, and then yeah, we'll use that to train our model. Okay, I guess we got through this. I was trying to rush through because we got started late, but I overcompensated. Now we finished a couple of minutes early, but I think that's okay. So we'll go ahead and we'll end here for now, and yeah, we'll see you on Friday. On Friday, I'll talk a little bit about our midterm exam, which I've posted already. I guess I'll talk a tiny bit about it, but I'll talk a little bit more about this on Friday as well. I posted a document, midterm1 topics.pdf, and so our first midterm exam is on Wednesday of week 4. We'll take it right here in class. You guys are here. I'm going to send out a seating chart, and so I guess I'll make an announcement. If you need to sit in a left-handed desk, let me know. But I think most, yeah. Well, anyway, and then so I'll send out a seating chart. It's a pen and paper exam. You will definitely need a calculator, and you will be allowed to have a single sheet of notes. Okay. So and these will be the topics. I'll talk about each of these things. Basically up through Monday's lecture. Okay, so today's stuff, the neural network stuff and beyond, will not be on the midterm. So from week 1 to week 3 Monday will be the content covered. Okay, all right. So we will we'll end here for today, and we'll see you on Friday.